go into the topic. So it is about wind power generation. As you know, this is one of the renewable energy. How we can extract electrical power from wind, and how we can make it more reliable. As you all know, uh, this renewable energy sources are intermittent in nature. That means they are not available always, and how much is available also is not in our hand. So how we'll make it intermittent? And wind power generation conventional system first we'll see, then we'll see one new research topic in the wind power generation, which we are working at IIT Ropar, that is bladeless wind turbines. As you know, all conventional wind turbines have blades, and these bladeless wind turbines work on a different principle, which and they don't require blades. So how they operate and what is their mechanism, what are their advantages, also we'll see and compare with the conventional wind power generation system. Okay. So wind power, as we all know, it is a renewable and abundantly available renewable source, and there are no emissions during operation, no water required unlike solar, which require cleaning. Otherwise, you will see a drastic reduction in the power generation. And main advantage with respect to population dense country like
All
India
the
is,
participants are requested to kindly switch off their microphone. Pitambaram has to kindly switch off your microphone.
hello,
So you can continue now.
yeah. So it uses little land. So with less land, I can generate more renewable power when I go for wind. So this is an advantage for population dense countries like India. Okay, and in India, already 39, more than 39 gigawatt has been installed currently. So first, before we see how we can generate power from wind, we must know how much power is available in wind, because that only I can extract. If there is no power in the wind, then I cannot extract. If there is X amount of power, then I can at max draw X amount of power from the wind, right? So for that, there is a theoretical study done which says the kinetic energy from wind, that is the, because wind, how is the power available? Because it is in the form of kinetic energy, because wind is flowing, so it has some kinetic energy, so that we are trying to extract, right? So the kinetic energy in the wind, in the with the same formula half mv square, if we try to derive, that is given by this half rho a v infinity cube, where rho is the air density, a is the rotor area where I am using which I am trying to extract wind, and v infinity is the wind velocity in meters per second. This is the power available, P naught energy available in the wind. Of this, can I extract the entire energy? The answer is no. We can extract at max 59% of the kinetic energy available in the wind. This is called as Betts limit. So this in 1919 it was derived that you can never extract full energy from the wind. Only 59 or 60% power can be extracted from the wind. Okay. So now we'll see the conventional wind power generation system. So the objective here is to extract electrical power output, because our grid is connected having 230 volt 50 hertz supply. I want to extract the power from the wind and convert it to the form of 230 volt 50 hertz, because that is our grid voltage and frequency. Otherwise I will not be able to connect it to the grid. Okay. So the objective here is how to extract power from the wind and convert it to 230 volt 50 hertz system, so that I can connect to the grid that is available for us. Okay. So to understand that, first we have to see what are the types of conventional wind turbines that are there. So one is called horizontal axis wind turbine and the other is called vertical axis wind turbine. As you can see from the photo, the axis of rotation is horizontal to the ground. So that is why it is called horizontal axis wind turbine. Whereas for the second one, the axis of rotation is vertical with respect to the ground and it rotates perpendicular to it. So it is called a vertical axis wind turbine. Both have their advantage and disadvantage. We'll briefly see what are the primary differences between the two. In horizontal axis wind turbine, since the axis of rotation is horizontal to the ground, the gearbox and generator, as you can see in the figure, have to be placed at the top of the tower. Whereas in a vertical axis wind turbine, since the axis of rotation is perpendicular to the ground, the gearbox and generator can be placed on the ground. So the tower need not carry the gearbox generator equipment. It only needs to carry the rotor blades. Whereas horizontal axis turbine tower has to carry not only the blades but also the other equipment which are gearbox, generator, converter, etc. So the tower required in a horizontal axis wind turbine need to be more strong, more sturdy, or need to be capable of bearing not only the blades but also the equipment. So that is why horizontal axis turbines are costly. Whereas vertical axis turbines are cheap because the blade that only have to be borne by the tower and all the equipment are placed on the ground. Okay. So vertical axis turbines are cheaper in comparison to horizontal axis wind turbines. Whereas if we see the efficiency, horizontal axis turbines are more efficient. Why? Why? Because it it the rotation of the blades is primarily dependent on the wind at higher altitudes, whereas vertical axis turbines rotate due to the wind right from the ground to the top of the tower. And we can observe that in normal locations at the ground until certain height there may be trees, houses, etc., obstacles which will hinder the wind flow. That's the reason vertical axis wind turbines will rotate at a slower rate in comparison to horizontal axis wind turbines and thereby giving higher efficiency to horizontal axis wind turbines. Okay, so horizontal axis wind turbines are more efficient but costly, whereas vertical axis turbines are cheap and but less efficient. So in small power installations, vertical axis wind turbines may be a good option because they are cheap, whereas for large power installations, mostly horizontal axis wind turbines are used because higher efficiency, that means higher power. And if it is a large power installation of the range of megawatt or gigawatt, then small efficiency difference will have a huge impact on the amount of power generated. Okay, so before we go further, we'll understand how the turbine blades rotate with wind. Because once the rotating motion is generated, we will couple a generator or an electrical machine uh, uh, mechanically coupled with the turbine. Then the machine rotor also rotates and we'll try to operate it like a generator. Okay, so how the turbine blades rotate? Suppose this is the cross section of a turbine blade which we call as an aerofoil, and wind, as we know, wind velocity as well as the direction is subject to change throughout the day. So when wind hits the turbine blade at an angle of incidence, at any angle I, then the turbine blade rotates But if the angle of incidence is changing, not all the forces falling on the turbine blade will contribute to the rotation of the blade. If you can observe here, we assume any angle and v velocity wind hitting the turbine blade at some cross section. Then we can see that the force that is acting on the turbine blade can be decomposed into two parts. One is the lift force, another is the drag force. And you can understand that this lift force, as the name suggests, it will try to lift or the road or rotate the turbine blade, whereas drag force is trying to pull the blade out of the turbine, which is counteracted by the hinges at the turbine. So this drag force component is not useful for rotating the turbine blades, whereas lift force component will rotate the turbine blades. So it is desirable that the wind hits the blade such that the lift force is maximum and drag force is ideally zero or minimum. Right? But as we know, the wind direction is subject to change even in between particular day. So we have to see that the lift force is maximized and drag force is minimized, so that maximum effort, maximum energy that is available in the wind is taken for rotating the turbine blade instead of acting on the hinges. Okay. So, for making the provision to increase the lift force and decrease the drag force, we have a control mechanism on the turbine blade, which we call as pitch control or pitch angle control. This control mechanism, depending on the wind direction, depending on the wind direction, we will rotate the blade along its own axis such that lift force is maximized and drag force is minimized. Okay, so by doing that, we are able to achieve higher efficiency and we are able to achieve higher speed of the turbine blades. And this control mechanism is also helpful when we have dangerously high wind speeds. In that scenario, we will rotate the turbine blades along their own axis such that the drag force is more and lift force is minimized, so that we will limit the speed of rotation of the turbine blades. Okay. And then there is another kind of control mechanism called stall control. All these control mechanisms are helping in maximizing the lift force or and minimizing the drag force for normal operation, and in higher wind operation opposite. That means maximizing the drag force and minimizing the lift force so that the rotational speed is restricted. So stall control means there are two types of stall control. One is passive stall control and another one is active stall control. In passive stall control, the blades while manufacturing itself are designed aerodynamically like the blades of a aeroplane, uh, or aerodynamically designed such that wind passes through them uh, at higher efficiency. That means higher lift force and minimum drag force. And active stall control, which is similar to pitch control, pitch angle is increased to reduce efficiency during high wind conditions. Otherwise, we'll try to reduce the drag force and increase the lift force in normal conditions. Okay. There is another kind of control called yaw control, which is not used frequently, but used in especially small rated wind turbines. Here, the turbine as a whole is rotated to align with wind speed such that lift force is maximized. right? So moving the or rotating the whole turbine from ground is a bit complicated, and it requires costly motors to achieve the same, and especially not preferred in very large scale installations. Large scale installations, it is not preferred, because when the turbine is rotated as a whole, then the blades are subjected to the wind, and it can cause some unwanted dynamics, which may cause sometimes that turbine structure to fall, tower structure to fall. So this is not generally preferred in large power rating turbines. So here we'll try to see some definitions. Tip speed ratio is defined as 2 pi Rn by V infinity. V infinity is the wind velocity, free wind velocity, and R is the radius of the swept area, N is the rotational speed of the turbine. Because the larger the turbine blade, the larger area wind it can capture, or it can rotate due to a larger wind area. So this swept area is the total area that one turbine will cover. So any wind in that area will help the turbine to rotate. Okay. And power coefficient, it is defined as power output from the wind machine by power contained in the wind. So how much power I am trying to get from the wind machine, that is the turbine, divided by how much power contained in the wind. So this will always be less than 60%, because we cannot extract more than 59%, as we have seen in the beds limit in the previous slide. So how much we have finally got practically. So that is a theoretical limit. So this will tell us the practically possible limit. And then aerodynamic efficiency. This is defined as useful power extracted from the wind by power supplied from the wind. So how much finally the power extracted from the wind by power supplied from the wind. So how much power we are able to extract at the end, that gives me aerodynamic efficiency, gives an estimate of that. So now we'll see, since we have understood how the wind turbines work, now we'll see how to generate electrical power. And not only electrical power, I want electrical power at fixed voltage, fixed frequency, that is 230 volt 50 hertz or 400 volt 50 hertz, that is required by the utility grid, and then connect to the grid or operate in standalone mode. There are two ways renewable power generation can operate. They can directly supply the loads by generating 230 volt 50 hertz, or I can also connect to the grid. When I connect to the grid, I will send power to the grid. Okay. So any one way I can operate them. So first we'll see what are the components for generating electrical power output and how to design them. Okay. So most of the wind power generation systems use a squirrel cage induction generator, which is written as SCIG, squirrel cage induction generator. Okay, this is the electrical machine that is used for extracting electrical power from the wind. So this is a turbine. This can be a vertical axis or horizontal axis turbine. If it is a vertical axis turbine, this motor will be placed on the ground. If it is a horizontal axis turbine, this electrical machine is placed on the top of the tower. Okay. So since the wind turbines rotate at very low speed, there most sometimes we use a gearbox. This diagram is a gearbox which will amplify the speed for the same power. Okay, torque will reduce correspondingly. Okay, so once I use a gearbox, I will get a higher speed at the other side, so that I will use a step up gearbox. and this other end of the gearbox is directly coupled mechanically to the squirrel cage induction generator rotor. So when this side rotates, the rotor also rotates along with the turbine. Okay. So once a mechanical input is given to an electrical machine, it will try to generate an electrical power. Of course, you have to connect some capacitors for reactive power since it is a squirrel cage induction generator. And so I can generate electrical power out of it. Since this is an AC machine, I will have an AC supply coming out of this squirrel cage induction generator whenever the wind turbine rotates. Okay, but I cannot give directly this power to this load, neither I can connect this AC supply to the grid. Why? Because this AC power that is coming is raw. Raw means the voltage and frequency of this AC power are uncertain. It depends on the turbine speed at which it rotates and other conditions. Okay, so how much voltage I will get and at what frequency I will get will keep on changing. So I cannot connect it with my local loads, which are fan, light, etc., which work at 230 volts. So I cannot apply a different voltage or different frequency supply. Otherwise, the devices may fail. Neither I can connect it to the grid because grid voltage is fixed. I cannot connect a different voltage source to the other source. Okay, so I must make this a stiff voltage corresponding to the grid norms, and then I will be able to either connect to the grid or supply the loads. So for that, what we normally do is we convert this AC power, which is not having any fixed voltage or frequency, into DC by using a three-phase full bridge converter, which is like a AC to DC converter. AC to DC we are converting. Once I have a DC supply here, I will try to make it a steady DC supply by using a capacitor on the DC side. What will this capacitor do is, as capacitor property is to maintain constant voltage. It doesn't allow sudden change in voltages. So it will maintain a constant DC voltage here. And this DC, I will try to use a DC to AC converter, which is controlled. How I am controlling the inverter or the converter used for DC to AC conversion? This inverter is controlled such that it will generate 230 volt 50 hertz supply. Exactly 230 volt 50 hertz supply. If it is single phase, if it is three phase, 400 volt 50 hertz supply. So once we generate fixed voltage, so this inverter has to be closed loop controlled. It is not controlled in open loop because this DC voltage will be varying depending on the voltage at the input. Okay, so varied voltage, I want fixed voltage. So I need a controlled converter. This controlled converter will try to make a fixed voltage, fixed frequency supply that I can connect to either to the grid or to the AC loads. Okay, if I have any DC loads, then this DC can be
Excuse me, sir.
directly up. Yes.
Sir, can you please again explain this use of three-phase full bridge converter?
Okay.
So this
So
is the interface. Why we are using AC? Because inverter is the AC is producing from the SCIG, and then we are using this full bridge converter just to convert it into DC. Why it is converting? We are converting it into DC.
we are converting into DC because the AC supply available here is not having fixed voltage, fixed frequency, right? So the objective is to convert this AC into a fixed voltage, fixed frequency supply according to our grid norms. So I need to use basically an AC to AC converter. So here we are doing in two stages. AC we are converting to DC, so that in DC frequency is 0. So any frequency supply comes here, I convert it to DC. Okay. So here there is no issue of frequency. Only issue is the magnitude of voltage. Magnitude depends on the AC voltage
Okay.
magnitude.
Okay, sir.
This magnitude varies, I agree, but I can control the inverter in closed loop fashion such that whatever be the magnitude within the range, I will modulate the inverter to generate fixed voltage, fixed frequency supply. Okay.
So to just to make the frequency constant or to make it zero, we are using this full bridge
Ah,
converter.
full bridge to make it zero.
Okay, sir.
I can use a diode bridge rectifier also here, but if I use diode bridge rectifier, it introduces harmonics, etc. So here it is a controlled rectifier, but job is same, AC to DC conversion. Okay. So once I generate fixed frequency, fixed voltage supply, I can run local load, or also I can connect it to the grid, whichever way is convenient. Okay. So since it is an unreliable source at the DC side, we normally use a battery so that even if there is no sufficient power coming from the wind, battery will supply. If I get excess power more than that is required by the loads, then I can charge the battery. So this will help in making the intermittent supply more reliable, more reliable. Okay. So these are the formula for the power generated from the wind. So half rho a V infinity cube is the power available in the wind into efficiency of electrical conversion, which is the machine and converters. Okay, a squirrel cage induction generator and converters, and then there is a mechanical transmission from the gearbox, and then CP is we already defined CP in the previous slides. CP is the power coefficient. So whatever power is available in the wind, not all power will be taken by the wind turbine. So how much ratio I am able to take, that that is first multiplied, then the efficiency. So this will give me the total power that is generated. Right? So approximately for slow rotors and fast rotors, it is given an empirical relation based on the diameter of the swept area and V infinity, that is the wind velocity, free wind velocity. So this will be the typical power output versus wind speed characteristics. After all the design, what are the things that we are interested in? First thing is input is the wind speed and output is the power generated, output power. That formula we have just seen. Okay, this P, generated output power. So if we see generated output power versus wind speed characteristic for a typical wind power generation system that we have studied, it will look typically like this. The numbers will differ from system to system, but the shape of the curve will typically look like this. So there will be a cut in wind speed below which there will be no there will be no power generated. This is because we have seen there are various efficiencies: electrical efficiency, mechanical efficiency. And in the electrical generator itself, if we see, there are some losses called as constant losses and some losses called as variable losses. Irrespective of how much power you generate, these constant losses have to be met. Those are fixed. Similarly, other electrical equipment or mechanical equipment will also have some fixed losses which will have to be met whether or not you generate power. So, if the power generated itself is less than those losses, then you will have no power generated. So there is no point in operating the system if the wind speed is less than what is called as cut-in wind speed. You will generate zero power. Once the wind speed increases, then you will start seeing a net output power after subtracting all the losses and all the efficiencies. Then you will have a output power available at the terminals, at the electrical side, with fixed voltage, fixed frequency. And as the wind speed increases, the power generated will increase. And once you reach rated wind speed, you will have rated output power. So in any given location, you have to decide on this rated speed. If you choose the rated speed very high, then correspondingly all the converter, motor, gearbox, all ratings will increase. And if that, suppose for this system, if I choose my rated wind speed as 30 meter per second and design my system, 30 meter per second speed wind may not come even for half an hour in one day, then all the equipment is underutilized. So you have to choose these ratings carefully. So then I am spending more and I will take more time to recover my input cost of the turbine and equipments. Whereas if I choose my rated wind speed very less, then I am losing the power uh, even in most part of the day. So this has to be a thoroughly designed based on the location. Okay, so for a given location, if 14 meter per second occurs for at least 60% of the day, then you can choose this as a rated output power on rotate speed. Then you will start seeing increase in the power generated. Once you reach rated power, you are already generating rated power. What is rated power mean? Means the converters, the turbine and the generator, every equipment is operating at its full capacity. When they are operating at full capacity, I cannot ask them to operate at higher than their ratings. So if, for example, the wind speed exceeds the rated wind speed, then I actually am capable of generating more power. But since my equipment are already reached the ratings, I cannot allow the turbine to rotate at higher than the rated speed. Then what should I do? We have discussed pitch angle control in the previous slides. So we'll do now opposite pitch angle control. That means we'll try to increase the drag force but keep the lift force at the rated maximum. Then onwards, I will generate only rated power. But pitch angle control is also limited. I cannot do it forever, right? So till some extent I can do pitch angle control and see that rated output power or ratings are not violated. And then once I reach a maximum wind speed higher than the called cutout speed, then I have to do some mechanical arrangement to lock the blades for further rotation. Right? Otherwise, it will damage the entire equipment. Once you cross the rated ratings, then generator will carry more current than its rating, converter will have more current than its rating, then all equipment will start uh, getting damaged because we are exceeding their ratings. Okay, so we have to do some protection to stop the turbine from moving. Okay. So this is how a typical power output for versus wind speed characteristic will look like. So this is how conventional wind power generation is done, and this is the energy distribution curve. So as we can understand, at the rated speed, rated power, all the equipment are fully utilized, so at their maximum ratings. So the fixed losses will be small when I draw at the full capacity. So I will have maximum energy generated. So now we will see why bladeless wind turbines when the conventional turbines are there and working fine, why we need to go for a new technology, or why there is a need for research in this topic called as bladeless wind turbines. So there are many advantages with bladeless wind turbines. First thing is installation cost is less. So always a cheaper option will be more commercially viable. So installation cost is less maintenance required. They do not create noise, and mainly it is safe for birds because the conventional turbines, because they rotate, this harm birds sometimes. So if there are no blades, then it is safe for birds. Okay, and it has smaller dimensions, so large number of installations are possible. As we can understand, in the conventional turbine, since the blade has to rotate, the next turbine cannot be placed very close to the first turbine. It has to be placed at a sufficient distance so that the blades will rotate without any obstruction. And bladeless wind turbine cost is less, and generating parts are kept on ground like a vertical axis turbine. Why it is of interest? This can be used with generation near point of use, and especially in hilly areas, these can be a good option, bladeless turbines. Okay. And they can be, since they are maintenance free, they can be placed offshore and offshore locations as well. And they are portable, they can have low maintenance, spatial efficient. Here in X distance, two turbines, here I can place more turbines, bladeless turbines here, and of course low cost, so and bird friendly. So because this is the thing with the birds, so since it will also help some this thing, so it is a good. So there is a company called Vortex Bladeless, which is manufacturing the bladeless wind turbines, and they seen lot of scope for bladeless wind turbines in India, USA, and Spain. They are trying to do research and manufacture bladeless wind turbines, and they have given the following advantages: height, weight, generation capacity, price. Yeah, we have an advantage with respect to bladeless wind turbines. Uh, so how the bladeless wind turbines work? So that first, if we understand, then we'll try. Then we can see how we can generate power from the bladeless wind turbines. So they work on the principle called as vortex-induced vibration. That means if wind or any fluid flows through a bluff body, suppose I keep some obstruction here and wind flows through it and hits it, and then there will be vortices formed. What will these vortices do is they create some pressure difference uh, uh, at the top and bottom. So if there is a pressure difference, what will happen is, if this body is allowed, it will tend to vibrate up and down. Okay, up and down, it will move like simple harmonic motion, up and down. So this is different from the conventional turbines, which are rotating in circular motion. If the wind hits the bladeless wind turbine, and if it is allowed to move up and down, it will move up and down. And if the more the wind flow is there, then it will move at faster rate, at faster up and down, okay, perpendicular to the flow direction. Okay. So this is how vortex, rotatory flow about an axis, no radial, low pressure at the center. It will create some pressure difference from the center to the top, so that the, if there is a pressure difference, the blades will try to move up and down due to the vortices. Okay. So, and the rate at which the turbine blade will vibrate is dependent on the material Stroll number, which is the material property, and V naught, which is the incident velocity. Of course, higher velocity will give faster vibration. And then there is something called as vortex shading frequency. Okay. What is this vortex shading frequency is, if the wind hits at this frequency, then the vibration will be maximum. It will be at resonance. At resonance, I will always have a higher higher amount of mechanical vibration that will come out of the turbine. So we have to carefully design, like how we are trying to design the conventional turbine system. Here we have to design such that we'll operate at resonance. When we operate at resonance, we'll have the maximum mechanical output in the form of vibrations, and that we have to convert it to electrical form, and that is the research area for electrical students. So this is the oscillation frequency must be synchronized with the voltage shading frequency. Then I will have the maximum output, mechanical output from the wind turbine. Okay. So this is the picture of a bladeless wind turbine. As you can see here, this one, whenever wind hits the blade or the turbine, it will try to vibrate. So the challenge is here, conventional machines, electrical machines are all working on the rotating to electrical or electrical to rotating motion. Here we are having a motion in the form of oscillation. So how we have to generate electricity from it? So there are two parts in any electrical power generation from mechanical. So first part is you have to have a field, because for generating electricity we need to have two components. One is the field, second is the mechanical motion, and perpendicular to each other. Then I will have a current or voltage generated perpendicular to both. So how we have generated, we'll see. Okay, so field arrangement is a critical challenge in this kind of, because the issue is wind speed is subject to change, right? Any direction it can come at any time. So when wind speed changes its direction, uh, the motion direction will change. When the mechanical motion has changed direction, field has to be perpendicular to it. So if I keep field in one direction, then for one direction wind only, it will generate electrical power output. Other directions it will not generate. Right? If it is in phase, or if the mechanical input and the field are in the same direction, then no power will be generated. Right? So that is the problem. All three have to be perpendicular to each other. What are the three? One is the mechanical input, and second is the field, third is the generated voltage. So how to ensure that? For that you have to ensure the field mechanism such that any direction of vibration can be converted into electrical energy. Okay, so this is the photo of the electromechanical arrangement. This is the mast body, which is free to vibrate in any direction. Using a spring arrangement, we'll allow it to vibrate in any direction. And then you have to place some field arrangement here. Some either permanent magnet or electromagnet has to be placed here, which will serve the purpose of field. When there is mechanical motion and field, then you will have an electric. If I place another coil there, then I will have a voltage generated whenever there is a change in the field or in the mechanical motion. Okay. So model and design. So and I should capture maximum power, because for any direction of vibration, because vibration will be perpendicular to the direction of the wind, and for any and direction of the wind will change. So in all directions of wind, I should be able to capture maximum power. Okay, so in this problem we tried different field arrangements. So as you can see here, magnets, I can use circular magnet, bar magnet placed in different configurations. My objective is, at the center there is the mast which is vibrating, so which will give me mechanical motion in all possible directions. So I should have a field perpendicular to the direction, to any direction, and a strong field, so that I will have, if I place another coil or either on the mast or in that field and vibration, if I place any coil, I will have an induced voltage in it. Okay. So, using the help of software ANSYS, we tried to analyze different combinations of permanent magnet arrangements, which will tell us how the field distribution is. So, what is the objective? Objective is first to have a maximum field change. Because if there is more change in the field, more d phi by dt, more d phi by dt, more voltage will be induced on the coil. So if I generate more voltage, then I can generate more power also. Okay. So if I see the my objective is at the center, I want maximum field distribution. If the coil vibrate little also, I will need to get maximum field change. So field profile is given with this color. Red means more field, blue means less field, and I want red to blue variation for small change in the vibration. For small vibration itself, more d phi by dt if it is there, then the coils if placed on the mast will have higher voltage induced. Okay. So if I see circular magnet, it is more flat, blue, all blue, same color. So I don't have see more flux change. If I put the magnets in circular fashion, bar magnets, then there is also only blue. So very less field is induced. That too, there is not much change. So if I placed a coil in the middle, then it won't have any voltage induced at all. This is a different type of circular arrangement. There is a bit difference, some from light blue to dark blue. Some improvement is there in the field change, but it is two drawbacks. One is it is only in one direction. So if the vibration happens in the same direction, no voltage will be induced. If it is orthogonal, only maximum voltage will be induced. If it is any other angle, the orthogonal component only will contribute to the voltage induction, so which will reduce. Okay. And then we tried different scheme by placing two magnets, not 180, not 90, but with an angle in between, which is 145 degree. If we keep it 145 degree two bar magnets, then we saw there is a huge difference from B max to B min. As you can see, 349 millitesla and 77 millitesla. So the difference is huge, 272 millitesla. Whereas for other angles, the difference in the B, the flux density is very less, is less comparatively. So we propose that you place two bar magnets 145 degrees to each other, then in the middle there will be a shaft. If it vibrates, then it will see maximum flux change, which will result in maximum voltage induced. Okay. So practically also we verified in the lab using the flux meter, and then we saw similar results at 145 degrees. Okay. So at 145 degree, if I place, then I will have maximum flux change, one advantage. But I want, but that there is a drawback. Drawback is this maximum flux change will occur only for one direction of wind, and for other directions there won't be any. There will be less effect. So how to cater for all 360-degree rotation, because a real in wind generation, I need I can have wind in all possible directions. So I need to have this kind of maximum flux change in all possible wind directions. So what we have done, we made it three layers, one, two, three, and each layer is tilted with respect to the previous layer by 120 degree. Like a induction motor, coils we place 120 degree apart, but that is for rotating. This is for vibrating. So we placed them 120 degree apart three. so that we cover all 360-degree. But for one possible wind direction, only each layer will give maximum. But for any other wind direction, every layer will give some component. So that net component addition of all the three layers will give me sufficient field change such that a sufficient voltage is induced in the coils. Okay. So for 145-degree layers, layer 1, 2, 3, I will have a flux change. If I have north to north and north to south. So if I make first layer north, second layer north, 120-degree, then I have more flux change. Whereas first layer north, then second layer I will keep south pole with 120-degree, but in that layer 145-degree two magnets. Then we are getting lesser flux change. So we propose NN arrangement, north to north 120-degree in different layers. In a given layer, two magnets with 145-degree displacement. Then we'll get maximum flux change. The same we have observed in the results as well, and then verified it. And then what about the length, breadth and height? If I change the dimensions of the magnets, how they are affecting the flux profile or field profile. So then we change different dimensions of the coil. As you can see here, from first and second, we changed only length. If we reduce the length, we are able to, we have a reduction in the B max and B min also increased. So the difference has actually reduced. Okay. So increasing length is better, and then breadth and height should be as high as possible, because if they are less, then the field flux density is reducing drastically. So breadth height, keep it as high as possible. Length you keep one limit maximum. Okay. And this is the field profile we have observed for the magnet. So as you can see here, you see inside some red is there, some blue is there, and then light blue. So different all colors you can see in between, right? So that means if the mast which is at the center, if it vibrates even slightly, it will see a flux change, huge flux change from red to blue. Red is maximum, blue is dark blue is minimum. So from red to blue flux change, if I see, I will see a maximum d phi by dt. So I will have a maximum voltage induced in the coil placed in the mast. So, as we know, even in electrical machines, permanent magnet based electrical machines are costly because of permanent magnets. So, we thought this is also like a machine which is not having rotational mechanical motion but vibration. So here also it should be possible to have a electromagnetic field arrangement that will help uh, reduce the cost, and also I want similar flux profiles which we achieved earlier, so that we have a lesser cost also and having higher voltage induced also. So for this we try because I have some voltage in my field. So here the at the center, I want maximum flux change. If I have, then it will generate more voltage. First, we tried with Goya coils, but here the if you see at the flux change at the ends. So if that the vibrates from here to here, 30 mm to 30 mm, then only it will see. Otherwise it will see flat. So it will generate any voltage, right? And then we modified this half coil system. Then we saw some flux change at the center. but this is not as high as at the ends. So then we modified the design further, configuration E, and then here we saw a better flux change, but the objective is to have maximum flux change at the center, so that even for small wind velocities and small vibration also, I will have a more generated voltage. Okay, this is the configuration 4, where it is changing from one extreme to another extreme, but at the center it is still 0. So then we tried to combine the previous configurations and finally achieve a huge flux change at the center. Right? So this is the configuration 5, which is the final design that was proposed. So here, if we use this kind of coil arrangement for field, we not only get maximum voltage induced, but also we are saving cost of the bladeless turbine, which is also otherwise cheap because there are no blades and the wires are placed on the ground. Along with that, we are also trying to get the advantage of using the permanent magnets. Okay, and then we are trying to do different configurations of field and armature, so that we'll have a better flux profile. So this is the hardware prototype which we tried to develop in our laboratory, where we place the coils here and then here permanent magnets. Okay. So this is the vibration amplitude that we were getting for a constant wind speed, and then for low to high wind speed, the 5, low to medium configuration 5, and low to high configuration 6. So these are the final designs that were given to enable higher voltage in uh, even for nominal wind speeds. So this is the conclusion of this bladeless wind turbines. They have a lot of potential in renewable power generation, and still further research is pending. We have only done the field part, and much further improvements can be possible. And even in the armature part, and power generation depends on armature and most importantly field design. So permanent magnet and electromagnetic field arrangements were discussed. For 18 tons coil, we have achieved 150 millivolt and 75 millivolt in the positive and negative half cycles in the laboratory. We are trying to scale this up by increasing the number of turns in the coils. Okay. So system scattering for all wind directions and increased power rating has to be designed. So this is the conclusion. Conventional wind turbine designs and their power generation techniques are discussed. Bladeless turbine technology is introduced along with its working principle and challenges. Few permanent magnet and electromagnetic designs are shown with their pros and cons. Future scope of work in this area is to increase the efficiency and cater for all possible wind directions. These are some references. Thank you.